Hi, here we are discussing about a project high-speed configurable floating point multi-precision processing element. Here we developed about the project which using for multi-precision floating point element. Here we discuss about a half precision, single precision, double precision method which using for FP16, FP32 and FP64. So this related work we have already developed in this way a configurable floating point multi-precision processing element for HPC and AI converged computing. Okay, so this is a model of this work in the website. Okay, so here we are already developed with double output ripple carry adders and parallel full adders and parallel half adders with approximate multipliers. Okay, so upgrade of this work, here we introduced a half precision method of FP16 only. Okay, so here the proposed approach shows the designs of working a pipelined fused multiple add or FMA processing element specifically made for FP16s, which is a half precision floating point data. This system is built to quickly do the calculations or equal to A times B plus C times D. Okay, the new design let us multiple two pairs of numbers and add the results together all in one smooth pipeline that is a much faster than old method. This kind of calculations is very important in digital signal processing like convolutions and FIR filters in matrix multiplications and in neural network tasks. It is also used in many other places like weighted sum and control systems. For example, the FIR filters uses this to get their output, and matrix multiplications need this product sum step again and again. This signal processors also use this fact method for many image and signal processing tasks. We made these architectures using a modular pipeline, which means each part like input processing, exponent checking, multiplications, alignment and addition, normalizations and outputs. Okay, so this work was developed in Verla HGLs and synthesized using a Xilinx FPGA with support of Vado software, and finally we compared all the parameters in terms of area, delay and power. Okay, now we can verify the paper. So this paper as per the proposed approach, here this is a proposed architectures. So here we integrate A into B and plus C into D. Okay, so as per this integrated architectures we have developed this work. Okay, and the base paper as per the precision level of half precision equal to 16-bit and single precision equal to 32-bit and double precision equal to 64-bit. So here half precision means we integrate this proposed novelty architectures with a 16-bit architecture only. A 16-bit, B 16-bit, C 16-bit and D 16-bit. Okay, so as per this flow of the design given in the paper, the figure 3, the architecture of proposed 3-stage pipeline multi-precision processing element, the same architectures we have integrated, but the little changes of this exponent and mantissa multiplications, we have modified the architectures. Okay, for novelty purpose. Okay, so this is the exponent process and this is the mantissa process, and this is the pipelining stages of alignment and adder tree process, and after that the final LZD process. Okay, so LZD means it's a least zero detections process. As per the number of zeros detections, it will be shifting the mantissa output and then it will be provide the final output. Okay, so that is a flow of the work. Okay, so here this work we integrated in Verla HGL. Okay, so here this is a code FP16 multi-operand P processing element. Okay, so here operand used A input, B input, C input and D input, and this is a multiplication result that also come with a 16-bit. Okay, so here we used for input processing input registers and sign processing, exponent, alignment. Okay, so all the codes available here, and this is a simulation report for this architecture. Okay, so here A, B, C, D input we given in a 16-bit vector, but internally we analyze this work in a particular bit size of the vector. Okay, so here in the half precision model, the exponent it will become with a 5-bit and mantissa it will become with 10-bit and the sign bit equal to 1. Okay, so as per that the A sign it will be considered 0, that means a 0th bit, and the exponent it will become with a 5-bit and mantissa it will become with a 10-bit, 9 down to 0. Okay, so here this one we are used for the verification process. So here it will be come with 4 sampling period. Okay, so why? Because here we are used for input registers and pipeline 0 registers and pipeline 1 registers and output registers. Okay, totally 4 pipeline architectures we have integrated in this code. If you are initialize any input in this architectures, it will be generated the output after the 4 clock cycle. Okay, so here you can verify the input which using this the cursor 3. Okay, so here I will be check the A exponent, B exponent, C exponent, D exponent. Okay, so here we need to add this value, okay, in a hexadecimal. Okay, then only we can analyze this work in a proper way. Okay, YE plus 0C and 16 plus 06. Okay, so output come with a 46. Okay, so here you can analyze the output in the multiplication results after 4 clock cycles. It will be come with a 45. Okay, and Mantis we can analyze it here 06C, right? So for analysis purpose we will be given a least numbers 6 into C. Okay, so it will come with 48, and CD also it will be come with a 6C. Okay, so 48 plus 48 equal to 90. Okay, so here output come with the 4590. That means 45 is the exponent and 90 is a Mantis. Okay, so as per this way we can analyze the output. So some of the cases it will be come with approximate output also. Why? Because we used a approximate multiplier with support of this paper. Okay, so that multiplier it will be copied from 12 cross 12 bit multiplier. Okay, so here they are implemented. Okay, so this multipliers we have used for this architectures. Okay, so it will be come with approximate, and the compressor model also will be used from this paper architecture, that also approximate model. Okay, so now we can verify the synthesized results. Okay, so here this is a synthesizer which using Xilinx ZCU104 FPGA. Okay, so here it will be take LUT 559 and flip-flop equal to 167, IO equal to 82 and PUBG equal to 1, and on-chip power it will be take for dynamic 0.027 and static it will be take 105, and here we can analyze the RTL schematic. Here it will be available. Okay, so here you can analyze it. So input it will become with A, B, C, D. Okay, and input processing, input register. Okay, so here input processing it will be splitting the input, which means sign bit, exponent and Mantis. Okay, and this is the input registers. After that a sign processing, multiplier array and exponent processing. Then it will become with a pipeline register 0. After that the alignment shifter and adder tree. Okay, so then after we move to pipeline register 1, and parallelly we calculate the LZD architectures, and this one is a exponent normalizations and Mantis normalization, and finally come with output selection and output register. Okay, so this is a complete architecture of the design. Okay, and we have written abstract document for this project, base paper abstract, improvement of this project, proposed title, proposed abstract, existing system, disadvantages and proposed systems, advantages, and related notes with the architectures. Okay, so everything included in the document for verification, and finally we come up with the literature survey and references. Okay, thank you.